In this video, we're going to look at Section 8 from the December 2017 exam for Math 121. The scenario is that there's a UFO that's been tracked, and we've measured the acceleration data for it. We note immediately that this is a piecewise function, where two of the intervals have relatively simple functions, constant acceleration of 5 meters per second squared and negative 30, and one interval where things are a little more complicated. The first thing that we're asked to do is simply sketch the graph of this function here. To be able to do that, we'd like to pick a reasonable scale. So we notice that negative 30 is going to be a value we'll need in the y-axis. We're also going to need 5. And this one also starts at negative 30, it looks like. And just to check here, a of 0 is going to be negative 30. We plug in t equals 0. And a of 4 with a little asterisk on it here because it's going to be just before 4. We're going to have negative 30 plus 5 times 4 is 20, so negative 10. Okay, so we have a range of negative 30 up to negative 10, then 5 after that. Let's put our axis on. We'll split the difference here. And sure, negative 30, negative 20, negative 10, 10, 20, 30. There's other ways to set this up, but we definitely need negative 30 and we definitely need 5 on our axes. So let's do the two easy ones first. Between time 4 and time 6, we're at 5, and that includes 4 but does not include 6. So 4 and 6, height 5, and includes 4, does not include 6. Likewise, from 6 to 8, including both ends, we have negative 30. So we'll have that. And the other element that we said there was there's going to be a function from 0 to 4. It's just linear. It starts at negative 30 and has slope 5, or goes up to minus 10 in that time. Either way you want to think about it. Starts here at time 4, it stops, and goes up to negative 10, like so. And that's it. That's our graph. It's simply translating what was given here into graphical form. Now, using that, we have to go backwards to velocity. We do know one thing, which is that at time 0, the UFO had a velocity of 70 meters per second towards the radar station. And then immediately, it was accelerating with a negative acceleration, so it was slowing down. And how do we capture all that? Well, the connection we're trying to build here is that the change in velocity over any time interval, here the entire 8 seconds, is what we get by integrating the acceleration. That'll give us the change in velocity. Now we can do this with formulas. We can actually go and integrate this interval and this interval and this interval. But given what we actually have in the scenario, we've already drawn a picture, and we can see that the integral is more easily calculated using areas. We can simply write out some rectangles here, for instance. Notice that this rectangle is 2 seconds by 5 meters per second squared. And that gives us a change of positive 10 meters per second. And likewise down here, we have 2 seconds, and we have a height, if you like, in this graph sense, of negative 30 meters per second squared, and that's going to give us negative 60 meters per second. It's a little trickier over here, but still not too bad. We can divide this into 2 blocks, where it is 4 seconds by negative 10, so this will be negative 40 meters per second. I'll just bring this up top so it's out of the way. And then the triangle is going to be a half of 4 seconds, and the height, careful, it's only this part that represents the triangle, that's negative 20. And so we're going to have negative 80 over 2 is negative 40 as well. Perfect, so we'll actually have negative 80 on that interval. So, just doing this graphically, we have negative 80. That comes from our little region like that, plus 10, that comes from our little region above the axis, and then minus 60, That comes from our region below the axis, that tall rectangle. And that in the end gives us negative 130, 40 plus 10 meters per second. Notice that's the change in velocity. Well, we started off going 70 meters per second. So the velocity at 8, actually let's do this formally. This integral from the fundamental theorem of calculus is the antiderivative. I'm going to write it out one way in a second and then show how it translates. We have an integral from 0 to 8. If we integrate it, we get the antiderivative at 8 minus the antiderivative at 0. But it's the antiderivative of the acceleration. Well, that's exactly what we mean by velocity. So this, in fact, was the inspiration for the fundamental theorem of calculus. If I know the acceleration over a time interval, I can calculate the velocity change at the start and end points. So for us, we just bring the v naught to the other side. So we have v of 0 plus this integral from 0 to 8 of a of t. And we know all these numbers now. V naught is 70, a of t is negative 130, or the integral of it, and so we end up with negative 60 meters per second, or 60 meters per second away from the radar station. And there we go. The key thing is being able to identify the integral and noting that we have to compute it differently on the three intervals. You could have done this with antiderivatives of the functions themselves here if you wanted. Just make sure that you broke it up into an integral from 0 to 4 with this function, then an integral from 4 to 6 with the next, and so on for the 6 to 8. All right, last but not least, let's sketch a graph of the velocity now. Well, we already have a head start because we know the starting value, it's 70, and we know the final velocity is negative 60. So let's do this as negative 60, do this as positive 60, so 70 is up here, negative 30. So 70 is where we start, negative 60 is where we ended. Now what else do we know? The translations between a function and its antiderivative is that over this time frame, say 4 seconds here, we know the change is going to be captured by this minus 40, that's negative 80. Oh wait, this number here, on those 4 seconds, we're going to have gone down 80. So from 70 down 80 is negative 10. That'd be around here, negative 10. And what does the shape look like? Well, the values here, the y values give us the slope. So the slope is initially minus 30. Towards the end, the slope is going to be negative 10. So we're going to have steep and then less steep. So something like that. Then what we have is a slope of 5 for the next interval. And we also know that after that slope of 5, we're going to go up by 10 meters per second. Well, we're at negative 10. So if we add 10 to that, we're going to end up exactly at 0. And because the slope is constant, we actually have a straight line there. Try to get that right. And on the last interval, we actually have a slope of negative 30. We go down by 60. Well, that's actually already factored into our shape here. That becomes our graph of the velocity.